This is our second video on conic sections, and in this one we are taking a look at ellipses. Now a conic section is just a curve of intersection between two surfaces. One of the surfaces is a cone, the other surface is a plane, sort of slicing through the cone. And depending on the orientation of the plane, we can get different types of curves. We've already looked at parabolas. In this video we will do ellipses, and in the third video we will take a look at hyperbolas. In this video, we will do or take a look at where the equation of an ellipse comes from. How do we define it? Do we also define it in terms of distances and focal points like we did with the parabola? We'll do a couple of examples and then we'll take a look at a few applications that are very nice. Now, an ellipse is actually defined in the same way that we did a parabola. We also focus on distances, and we also have the idea of a focal point inside the ellipse, or in this case, more than one. Now, an ellipse is defined to be the set of all points x, y, for which the sum of the distances to two fixed points, called the foci of the ellipse, is constant. What exactly does this mean? Well, it means if we have 2 points in space, these are our foci, and we have some third point, let's say xy. Suppose the distance from xy to the first focus plus the distance from xy to the second focus is some value like 10. What we are trying to do is we are looking for all other points in the plane where the distances or the sums of distances toward the foci is also 10. Then we connect all of these points and eventually they trace out the entire ellipse. I'm going to show you with an animation. You can also click on this link or just copy the link. It takes you to a Desmos animation where you can play around with different values for the ellipse in the equation. You can also look at the animation to see how the distances are affected if you change your x and y values. And also just to get a better or a general idea of what will change when you change certain things within the equation. So I'm going to play it to you now, and all of the points that we are going to be tracing, we will be moving around that point xy. The main thing is that the distances from our point to the two foci, if we add them, these distances will remain constant. And all of these points, they trace out that shape of the ellipse. All right, so let's start by specifying the two coordinates. We want to again get an equation for an ellipse like this. Specifically, we make it easy for ourselves. We start with an ellipse centered at the origin with the two foci on the x-axis. So we are going to give them coordinates. Let's say the first one is at negative c0, and the next one will be at c0 for some real positive number c. Then next up, we are taking a look at the distances that need, the sum of the distances that need to be constant. So we first take our distance from xy to the first focus, negative c0. The formula there will be the square root of the x coordinates difference squared plus the y coordinates difference squared. So this will be x minus c squared plus y minus 0 squared. And then we add it to this distance from xy to the second focus, and this will also be the square root of x minus c squared plus y minus 0 squared. And we've defined, or we are trying to define it in the way that this sum of the distances has to be constant. So we are going to say this is equal to sum k. Now, we are going to take this. This actually describes everything that's going on involving our variable point x, y. So we are going to take this and try to rework it and simplify to see if we can get a formula or an equation that describes in a quick way what's going on. So if we do this, what I'm first going to do is I'm taking the square root x plus c squared plus y squared, the first one, and I'm solving the equation for that square root. So I'm taking that green square root over to the right-hand side, which gives us k minus the square root of x minus c squared plus y squared. We want to get rid of these square roots because they make our lives more difficult. So what we'll do in this case, we can't get rid of both of them at the same time, but we can square both sides of the equation to at least get rid of the first one. So if we do that on the left-hand side, we get x plus c squared plus y squared. And on the right-hand side, we get k squared minus 2 times k times the root, plus then the square root squared will cancel, so we will only have left x minus c squared plus y squared. So again, we can expand a little bit here. We will get x squared plus 2xc plus c squared. We keep everything else the same. Inside the square root, we don't simplify just yet. And then the last part, we can multiply out that bracket, and it's going to give us x squared minus 2xc plus c squared. What we are going to do at this stage is just at least see if we can cancel some terms that are the same, because this is starting to look like a bit of a mess. So on both sides of the equation, we have x squared, so those cancel. We have c squared on both sides, so those cancel. And we have y squared on the left and on the right, so those will cancel. And then we can just write it out a little bit neater. So we have like terms that we can add. The 2xc, there's another negative 2xc on the right. We can bring it over to the left. This will give us 4xc. And on the right, we have k squared minus 2k times that square root. So now's our chance to get rid of that second square root. I'm going to take that term, 2k times the square root, over to the left-hand side and everything else over to the other side so that we can square the square root away. So 2k times that square root will be equal to k squared minus 4xc. We are going to square both sides. So on the left, we will get 4k squared. Square root will cancel. I'm also multiplying out that bracket. So we will get x squared minus 2xc plus c squared plus y squared. And on the right, if we square that, just stick with me. It looks terrible right now. But if we square the right-hand side, we get k to the power 4 minus 8k squared xc plus 16x squared c squared. Now we are going to simplify this a little bit, and we have to make it look a little bit better, because this, even though it does represent what's going on, is not very user-friendly. It doesn't look like something that we can directly quickly see. What will the foci be? What's the major axis? Everything that we are going to look at for an ellipse, at the moment, we cannot see it directly from the equation. So I think at this stage we can all agree it is more of a mess than it is something to work with. So first what I'm going to do is I'm going to multiply out the brackets on the left-hand side of the equation. We will get 4k squared x squared minus 8k squared xc, which is useful for us because there we also have a minus 8k squared xc. So at least this can cancel. So first let's do that. Going to do this very quickly, but you can pause and you can write this out as well on your own just to confirm that you get the same, but those two terms at least will cancel and we can do something with that. Now the other idea that I had with this is an ellipse almost looks like a circle that was stretched a little bit too much in one direction, right? What does the equation of a circle centered at the origin look like? It is x squared plus y squared is equal to the radius squared. So in those equations, our x squared and y squareds, or the terms containing them, are on one side of the equation and everything else is on the other. So let's at least work towards something like this. Okay, we do have terms with x squared in them. It's this 4k squared x squared, and there we have a 16x squared c squared. So that's the first thing I'm going to do, is I'm going to take those terms to the left-hand side and factor out that common x squared, just to see what's left. So what will be left is the 4k squared minus 16c squared. So we have our x squared term. We are going to use our y squared term. There's only this one, so we don't have to factorize. We are just going to also keep this on the left-hand side of the equation. And then everything else, this 4k squared c squared, that's all we have left to work with. And the k to the power 4, we are going to keep on the right-hand side of the equation. So we get k to the 4 minus 4k squared c squared. Not ideal yet, but a little bit closer to what we are actually looking for. At this stage, I'm going to go back to our sketch. What did we use in our equation to get to this point? Well, we used the two foci, right? We used C0 and negative C0. We also used our random point on the ellipse, xy, and we used the fact that the sum of these distances add up to some constant k. This is what brought us to the equation that we see on the screen now. What I'm going to do is now introduce a few new points that we haven't used before. We haven't looked at this point where the ellipse intersects the x-axis, as well as this one, which is just the same distance but on the opposite side. So let's give this a name. Let's call this point A0, and let's call this point negative A0. Because these points also lie on the ellipse, they also have to satisfy the condition of the distances. So the sum from A to the one focus, let's draw it in. So from A to the focus on the left, plus this distance over here to the second focus, has to also be equal to k, right? So what does this actually mean? Well, one thing is if we have this distance plus this distance, it has to be equal to k, and this value is going to be equal, let me just move that one over there. What would happen? This short distance between the point that we are looking at and the focus is exactly the same as this little distance over there. But if we put all of this together, what does it actually give us? It gives us the full distance from this point to that point. Now we know the distance from the origin to that point is a, so we are just doubling it, meaning that full distance will be 2a, and that's equal to our constant, that sum of the distances to the foci. All right, long story short, we can now use this fact and replace k is equal to 2a in the equation that we are working with. Where will we be replacing it? Over here, over there, and over there. So let's see what we get. We will get x squared is 16a squared minus 16c squared. Nice common factor there. Maybe we can use that. Then 4 times k squared is 4 times 4a squared. So here we also get 16a squared y squared. It's looking good. On the right, we get 2a to the power 4, which gives 16a to the power 4, minus 16a squared c squared. I hope you are seeing where this is going. There's a common factor of 16 right throughout our equation. So we are going to divide by 16 and see what we are left with. So now we have x squared is a squared minus c squared plus a squared y squared is equal to a to the power 4 a squared c squared. There's a lot of algebraic manipulation going on here, so I hope you can still follow. But the main thing is we are trying to look for patterns, anything that we can group together, anything that we can factor out, anything that we can rename, which is going to be our next step. What I'm seeing almost featuring here is this bracket, a squared minus c squared. I'm seeing almost the same thing here if we were to factor out a common a squared. So let's do that. If we factor out a common a squared on the right hand side, we also get this a squared minus c squared. Okay, that's good. This is something that they have in common, and we are going to take a look at our sketch over here to see if we can even simplify it further by maybe replacing this bracket with something involving our y-intercept point. We are so close now. We have to look at our sketch again. We have used, so far, the two foci. We have used the random point on the ellipse. We have also given a name and used the x-intercepts, but we still haven't looked at the y-intercepts. So let's give this a name. Let's say that coordinate over there is b0, and then obviously this coordinate down here will be negative b0 because it is symmetric. Let's see if we can use that in order to simplify our equation even further. Now, what do we know about this point? This is the y-intercept, or one of the y-intercepts, and it occurs when x is equal to 0. So we're going to do that in our equation. If we set x is equal to 0, we get a squared y squared is equal to a squared times a squared minus c squared. And we know a squared is not equal to 0 because clearly here a is not 0. So we are allowed to divide on both sides by a squared. And this gives us y squared is equal to a squared minus c squared. Can you see how it all comes together eventually? We know something about this. This is not just any y, it is actually the b value that we specified here. If we say this y-intercept over there occurs at height b, we can rewrite this equation and we get b squared is equal to a squared minus c squared. What this means eventually is we can replace this in our equation with b squared. Great. Does it make sense if we can do that? Well, a is bigger than c, so a squared will be bigger than c squared. So this will definitely be a positive number, which aligns with something being squared. Makes sense? It works for us. We can use this. Let's replace the a squared minus c squared. So we get x squared b squared plus a squared y squared is a squared times b squared. One of the standard forms of the ellipse that we write the equation in is where the right-hand side is equal to 1. So we are going to take our right-hand side, the a squared b squared, and divide it by itself, and we're going to do this throughout our equation. And let's see what form we actually eventually end up with. It looks a lot neater than the one we started with, by the way. So eventually, if we cancel the terms at the top and at the bottom, we get x squared over a squared plus y squared over b squared is equal to 1. Very simple. Also includes almost all the information that we need in order to sketch and to know what our ellipse actually looks like. So let's recap quickly. So there we have it. This is our equation for an ellipse centered at the origin, where we know our foci lie on the x-axis. What can we take from this equation? Well, the first term is actually telling us about the intercepts or the x-intercepts. Remember, if we make y equal to 0, this term falls away, and so x squared must be equal to a squared. So our x-intercepts will be at x is equal to a and x is equal to negative a. Also, if we want to find our y-intercepts, we can read it directly from the equation. Why? If we let x be equal to 0, then we only have y squared over b squared is 1. So y squared must be equal to b squared, which gives us y-intercepts or values of y is equal to b or negative b. So these denominators really already give you a very good indication of the shape of your ellipse. Right. Then we know it's centered at the origin because this is how we derived it. But we also have our foci. These will lie on the x-axis at c and at negative c. So x is equal to c here, x is equal to negative c there. How do we find the value of c from the equation? Well, we have to use the part in our formula or in our equation where we simplified it a little bit. And remember, we did this by saying that b squared must be equal to a squared minus c squared. So this is the part that we use to simplify our equation, but this is also a formula that we can then use to calculate our c, given we know what a and b is. Another thing that we can take from this is the fact that b squared is a squared minus c squared. So b squared is definitely smaller than a squared, meaning b is smaller than a. What's important about this fact is the shape of the ellipse. Remember, we said a tells us where it cuts the x-axis, right? At a and at negative a, and b is where it cuts the y-axis, b and negative b. So if a is bigger than b, it means the ellipse is wider in the direction of the x-axis than it is in the direction of the y-axis. And this brings us to the idea of major and minor axes. In this case, because the distance from the origin to the furthest points along the x-axis is bigger, we call the x-axis the major axis of the ellipse. And so we call the y-axis the minor axis, because the ellipse is shorter in the direction of the y-axis than it is in the direction of the x-axis. Let's take a look at one final example of also an ellipse centered at the origin, but with a different major axis. The equation that we are looking at is x squared over 4 plus y squared over 9 is equal to 1. It's already in standard form because the right-hand side is equal to 1, and we can recognize it as an ellipse because we have a term with x squared being added to a term with y squared. Again, it looks almost similar to the circle equation, but we have different coefficients for x squared and for y squared, which hints at it being an ellipse. Right, if we apply all of the previous knowledge that we have to this equation, we said that this value over there, our a squared, tells us about where it cuts the x-axis. And this value associated with our y squared tells us about where it cuts the y-axis. So let's set up our system of axes here. The x-intercepts will be at plus or minus 2, so we take the square root. And the y-intercepts will be at plus or minus 3. So let's indicate them on our set of axes. And then we can simply complete the shape. We know we are dealing with an ellipse, so we can draw our ellipse passing through these points. Now, if you take a look at the ellipse as it is here, would you agree with me that the longer side of the ellipse is definitely associated with the y-axis and not the x-axis? Simply the distance from the origin to the furthest points here will be 3, but in terms of the x-axis, it will only be 2. So major axis is definitely the y-axis. Then we need to calculate or to find where the foci of the ellipse are. So now we use that formula, b squared is equal to a squared minus c squared. We have values for a as well as for b, so we can plug those in. We get 9 is equal to 4 minus c squared, and we can solve this equation for c squared, which gives us 9 minus 4, which is 5. So the value of c will be the square root of 5. Again, where we place the foci will make a big difference, and it depends on what the major axis is. In this case, we saw the major axis is definitely the y-axis. So this is where we will draw our foci. So the foci will be at y is equal to square root 5 and at y is equal to negative square root 5. So again, a lot of things happening, but from the equation itself, it's very easy to find the intercepts, and it's even easier to find the foci, as long as we keep in mind which of the axes is the major axis.